All right, so we're going to talk about this. Why don't we first do this, though? So today, we're talking about current source matching and emitter coupled pairs. I have no announcements to make. I'm late because I had a visitor, and I was having lunch with them, and I couldn't get out of there fast enough. But the lecture topics today are going to be current source matching, op-amp review, and emitter coupled pair. But the aside that I want to talk about in talking with some of you in office hours, also talking to the TAs, is this DC bias operating point here that I want to make sure that you guys are comfortable doing. And maybe that's what some of the issues were. You know, these are complicated looking circuits. But in the end, they're really not that complicated once you know the procedure of how to analyze these sort of things. Let's talk about getting the DC operating point. And normally when you want the DC operating point, what you're really trying to do is get all the voltages at all the nodes and all the currents through all the branches. But you don't really need to do that. You really need to do that mainly for the devices that are in the signal path, because those are the ones that you want to determine GM or R0 or R pi from, or if you were MOS, right, still GMs and that sort of thing. So say I wanted to find out what V0 was. And that's the DC operating point, the DC output voltage. How would you go about doing that? What's the key to doing that for a circuit of almost any complexity here? So what's key? The key part of your procedure is you need to find a resistor with a well-defined voltage across it. Okay? And that's basically all you have to do. So, like most circuit analysis, it's a recognition problem. You're trying to look and see if you can find that resistor that has a well-defined voltage across it. So let's go ahead and try to do that for this very circuit. Let's go all the way back and find that circuit. Okay, so if we're looking at this circuit, what does that mean? So here's the voltage that I'm looking for. I want this voltage right there. I want that V out. And I see a resistor right here. Okay? And so if I knew what current was going through that resistor, I could probably figure out what that voltage is if I knew what the voltage was right here. Okay? But I got a bunch of problems. I don't know what the voltage is right here. I also don't know what the voltage is across this VCE of this transistor or the VCE of that transistor. Okay? Do you understand why I can say I don't know the voltage across there? Okay, what voltages do I know in this circuit? Could someone tell me? So I know VCC, obviously, right? That's 10 volt. I know ground, that's 0 volts. Right? So those are known voltages. But that's not enough. I need to know some other voltages. So what other voltages do I know in this circuit? Exactly, right? So one thing that I know, a well-defined voltage, so I guess I'll list my well-defined voltages here. I know VCC is 10 volts. I know ground. But I also know what the VBE on is of a transistor. Okay? And so what is the VBE on? Right? So if I ask that question, what is VBE on? Is it 0.6 volts? Or is it 0.7 volts? Right? So that could be a question someone will ask. What is VBE on? Okay? Here's my answer to that question. Who cares? Right? 0.6 equals 0.7 to me. Doesn't that equal, don't they equal the, I mean, they're the same number to all of us, right? 0.6 equals 0.7. Who cares if it's 0.6 or 0.7? So if someone doesn't give you VBE on, just assume something. Assume it's 0.7. I generally assume it's 0.7, right? Other people will assume it's 0.6. It's not going to change your answer too much, right? Because you're looking at 10 volts at VCC. So VCC here is 10 volts. 0.1 volts out of 10 volts is nothing. Very small percentage there, right? So who cares what that VBE is there, right? And so what we're going to be able to do is say that VBE is a known voltage. And so that wherever I see a base to emitter for these transistors, that's a VBE on. That's 0.7 volts. Okay? It doesn't matter which transistor I look at. Oh, look, here's another transistor, another VBE, 0.7 volts. Hey, here's another one. Right? 0.7 volts. And all of them are 0.7 volts. Wherever you see a VBE, it is 0.7 volts. Or 0.6, whatever you want, but who cares again, right? Yes?
So in general, can we always assume all the transistors are saturated?
Exactly. So that's the other thing that you need to be careful with. Okay, so I'm flopping around with my 0.7 volts, but you're exactly correct, right? You cannot say it's 0.7 volts if the transistor is cut off or if the transistor is not in saturation, right? Or sorry, this is bipolar. So if the transistor is saturated, you cannot say it, right? Forward active. You can only do this if the transistors are forward active. So I should make that disclaimer there. For a forward active transistor, you can assume that. If not forward active, you cannot assume this. So we have to look at different transistors here and what we can assume, right? And you have to go about through this circuit and figure out whether all the transistors are in forward active or not. Okay? So how can you tell whether a transistor is forward active or not? So say I pick this transistor Q2 right here. How do I know whether it's forward active? Let me put that in green. So if it's forward active, then I'm going to want to say that I've got a voltage across here that's 0.7 volts. But what if this collector voltage drops too small, right? So you're basically looking to make sure that this voltage across here is higher than 0.2 volts, right? Which is VCE sat. Do you guys remember that at all? Remember your device physics that you had from the beginning of this class? Those lectures you had in the beginning? So it's all in those lectures. So let's go up and take a look at your bipolar review here. These are the lectures that you saw earlier in this class. Let me get to it. Right here. So if you look at the earlier lecture, you had these things here, right? So if you have a transistor, a bipolar transistor, and it's forward active, then the equivalent DC model for it is a VB on is about 0.7 volts, okay? And then the VCE should be something larger than 0.2 volts, okay? And if it drops to 0.2 volts or tries to get below that, it's not going to get below that because the transistor will get out of forward active and it'll suddenly become a saturated transistor, okay? But those are special cases that you'll see very, very rarely. Do I even have in these notes so that's forward active BJTs. Let's see if I even have the other cases here. Yes. So here's the saturation region. All right, so these are all in those notes earlier there. So if you're in saturation, then what happens is you get a VBE that's higher than 0.7 volts because now it's pulling a lot of current, right? You saturate a transistor, you're kind of maxing its collector current. And so maybe your VBE is a little higher, 0.1 volts higher, okay? That falls into the who cares category to some degree, but if you want to be absolutely right, then if you're using 0.7 volts for forward active VBE, then in saturation it's 0.8. Right? But in the end, you're going to have, saturation means both of these junctions are on, right? And so in the end, if I wanted to look at VCE across this, if that's 0.6 volts across VBC, and it's these different voltages because you got different doping levels between your emitter base and base collector, right? That's where that comes from. If you don't understand that, then you should take 130 to get that. You don't need to understand that. All you need to understand is that when it's saturated, you got 0.8 volts dropped from VBE, and you got 0.2 volts dropped across VCE. Okay? If you have something like that, then the bipolar transistor is saturated. Okay? But the main thing to remember is that VCE is probably not going to go below 0.2 volts in any circuit that you have. And so when you're doing your circuit analysis, if you end up seeing the voltage trying to get below 0.2 volts, you're going to have to just clamp it at 0.2 volts there between VCE of the transistor, between collector and emitter, and just solve the circuit with 0.2 volts there. Okay? And when you're cut off, there's no rules. So if it's in cutoff, then I just have an open circuit throughout this whole thing, and then the voltage that it takes on is decided by the circuits around it. Okay? But if I have a forward active transistor, I know I've got 0.7 volts across VBE, and that's a very stable voltage. If I have a saturated transistor, I know I've got 0.8 volts across VBE and 0.2 volts across VCE. Okay? So those are a couple things to remember there. And these are all in that first day lecture thing. So you can go back to that, or second day lecture. You can go back to that and just refer to that if you want to remind yourself of what these transistors do for DC bias points, if they're forward active or not. But let's just sort of continue with this here. Right? VCE's got to be greater than 0.2 volts for that to be forward active. That's something we'll verify later on. Okay? We can't verify it immediately. Right now, what we have to do is assume that everything is saturated. Everything is forward active. Okay? So you start out with this assuming everything is forward active. And yeah, you could be wrong with that assumption. You could go through the whole circuit, find out one of these transistors is saturated. And if you do that, you have to start over again to account for that saturated transistor. But 9 times out of 10, if it's a correctly designed circuit, which is what you'll see if someone in industry gives you a circuit, they're going to be forward active. Of course, in a class like this on a midterm, right? It's not 9 times out of 10, right? We'll try to trick you by putting one transistor as a VCE in saturation, right? We might do that to you. So you have to know what's happening there. So let's look at this whole circuit, right? This looks like a complicated circuit, but if you just assume everything in this circuit is forward active, you'll see how simple this is, right? I'm assuming everything is forward active, which means I'm assuming I have 0.7 volts across all of these VBEs. And I guess just as an aside, just to make sure everyone understands, why is it that we can make that assumption that the VBE is so stable? It's because of this. Because if you plot the collector current of a bipolar transistor versus VBE, right, you know the equation for that collector current. You know that that's going to be equal to some IS times an XE to the VBE over VT. It's going to be related to this, right? So it's exponentially dependent. And so what happens is that when you hit VBE on, this thing just skyrockets like that. It looks like a diode pretty much, where that's your VBE on voltage, which is 0.7 volts. And so when I look at this, if I had a current equal to this, right here, what's the voltage across my base to emitter? Why, it's 0.7 volts. Okay? If I had a current equal to this, oh, it's still 0.7 volts. It may be 0.70005 volts or something, but it's still 0.7 volts. So in this case, VBE is a very well-defined voltage if the transistor is pulling its current, because it doesn't matter how much current is going through that transistor, that voltage is about VBE. Okay? And the amount of current pulled through that transistor is determined by other elements around the transistor, not by the transistor itself. Okay? So that's why we can say VBE is a very well-defined voltage for a forward active transistor. Now, why is it we can't say VCE is a well-defined voltage? Okay, well, I can do the same kind of thing. I can plot the collector current versus VCE. So this is a plot you know how to make, right? This looks like this. Right? And so if I look at this and I say, okay, suppose I've biased it to this, and I wanted a specific current here, right there. If I wanted that current, you can see that I could get approximately that current over a range of voltages that's quite high. Right? So the slope here for that current is not going straight up. That's a pretty flat slope across there. That means many VCEs can support that current. Okay, so VCE is not a well-defined voltage. Okay, so not well-defined for a given current, and this is well-defined. Okay, so I go back to this. Yes?
We're doing all of this in BJTs, but for MOS, the graphs look the same, yet we don't have a well-defined VGS.
Yeah, that's because the VGS, it's because you can design your MOS. MOS is more designable is what that comes down to, right? Depends on your W over L, depends on a lot of things. Plus, it's not as strong a nonlinearity as the exponent, right? An exponential is much stronger than the square law of an MOS. So that's why with MOS, it's not going to be as easy as just saying 0.7 volts. With MOS, you're going to have to calculate what that is based on the current going through it. But those are closed-form calculations, right? You can make those calculations. Yes?
So all the math that we've done for BJT is largely in the forward active region. We have to assume that any of these was a saturation. How do we get the current for that? We just look at the graph and see.
No, if it was in saturation, then I would just make the voltage across VCE of Q2 0.2 volts. I would make the voltage across VBE 0.8 volts, and then I would just solve everything that way. Right? If it's forward active, you can't say what VCE is. Something else is going to determine that. If it's saturated, VCE is 0.2 volts. Okay? But in most cases, it's not going to be saturated. In 9 out of 10 times, it will, 10 out of 10 pretty much, right? It'd be forward active if someone designed it correctly, right? But there's cases where someone hasn't designed it correctly, like me on a midterm, or someone at work, right? And so you might have to be careful with that. Yes? No, I assume all are forward active.
But if you do the forward active first and determine that one of those is saturation, and you have to go back and do everything again, can you assume that all of them are in saturation?
No. You assume just that one is in saturation. It's going to be an iterative process, right? So it's a guessing game. It's a guessing game from the beginning, but it's not a bad guessing game. Because like I said, 9 out of 10 times, it's forward. All the devices in the circuit are forward active, if it's designed right. So it is. I think this is the leap you have to be able to make in a class like this, in this type of material. You have to be comfortable with taking a guess, seeing if it's right, and then going back and fixing it if it's not. Okay, this class requires that. And that's the only way to handle these big circuits. Yes?
How do you determine that one resistor out of all of that is in saturation?
Well, you find so you go through assuming everything's forward active, and then suddenly you find an inconsistency. So you find that, okay, it's impossible for that to be forward active because, generally what's going to happen is, you find all these transistors, then you find out this voltage at that node, and you find that voltage is less than ground, right? And then you say, uh-oh, that's impossible because the emitter's at ground, the collector can't be less than ground, so it's going to be saturated. And so what you do is you just put 0.2 volts across that, and then you solve it again, knowing that that's 0.2 volts. Okay? And it's very similar for MOS, except as was stated, you got to calculate the VGS. Okay, so MOS is harder. So the two things are MOS is much easier when it comes to small signal analysis, right? Because you have all these infinite impedances. You don't have to worry about loading as much, but it's much more difficult to get the DC operating point in MOS. Okay? So let's go through and get this DC operating point. Right? I got 0.7 volts across here. I have 0.7 volts across here. But this is still an undetermined voltage here. So I do not know how much current is going across that resistor RE8. I really need to know how much current is going across that. can I determine better what this voltage is right here? Well, yeah, I can. Because if I look at this, this is 0.7 volts right here. That's 0.7 volts. So if I can figure out what the current is going through this RE5, then I know exactly what this voltage is right here. Okay? But oh no, look at this. That's a VCE. That's not a well-defined voltage for me. Okay, so I still can't do anything at this point. Right? But then I look at this thing right here. Okay, there's Q4. That's diode connected. Oh, all right. Well, I know that's 0.7 volts across here. But that doesn't really help me too much, because I still have this transistor that has an undefined voltage that still doesn't allow me to get the voltage across this RE5, or at least current through that. Turns out I don't want the voltage across RE5. I can't determine that, or I do want that, but I can't determine that just off of this. The way to determine that is to recognize, oh, this right here that's a current mirror. And then I look down here. That's another current mirror. Okay? And so now I can do this. So now in order to solve this problem, I first need to get this IREF. I get that current IREF because I can do that, right? I've got VBE on as 0.7 volts across Q1. And so just to get IREF, I can write down the expression IREF is equal to VCC, which is the voltage at the top of the resistor, minus what I'll write as a VBE on, which you can put in as 0.7 volts, but I recommend you don't put any numbers in yet because, right, then you'll complain about doing too many calculations, right? And so that's just divided by RF. Okay, so that's IREF going through this. And then I can look at this. Oh, this is a current mirror. That's a current mirror, so that current right there is also IREF. Right? This is a current mirror. It should have a nice large output resistance there. It should be shoving IREF through that device as well. Okay? And then I look at this. Oh, there's another current mirror right here. So this current, it's also IREF. So one little equation has given me the current through all these branches here. And then I look at this and I say, oh, okay, I know that IREF is going through RE5. So I know that the voltage right here, which I'm going to call VB of 8, the voltage at the base of transistor 8, VB of 8 is going to be equal to a VBE on, which is across Q6. That's just 0.7 volts, plus the current IREF, which I just determined from up there, times the resistor value RE5. Okay, that's my VB of 8. So now I know the voltage right here. Okay, and if I know the voltage right here, and then I have to determine what the current is through this. What's the current here? Well, this is a current mirror. That is mirroring the current here too. This transistor Q7 is doing the same thing as Q3. It's repeating that current. This is also IREF. So all the currents in this whole thing, because I'm mirroring them everywhere, are IREF. Right? And so if I know IREF, oh, I know the voltage across RE8. And so I can finally write that the voltage V naught at the output is going to be equal to VB8 plus this voltage, which is a VBE on, plus the voltage drop across RE8, which is now IREF, times RE8. And that's the answer. And I can expand this because I know what VB8 is. VB8 is this thing, so this is going to be 2 VBE ons. If I add this VBE on with that from VB8, and then plus IREF times RE5 plus RE8, and that's my answer. Okay? So it looks like a pretty big circuit. But if you can recognize part of the parts of things in this circuit, right? If you can recognize that that's a current mirror, that's a current mirror, this is a current source that's being created by the V bias, right? This is basically a V bias that was generated right here by that current mirror. It's giving that V bias to this transistor and to that transistor. And if these transistors are all sized the same, which they are, then you have Iref going through all of these things, and I can easily determine what that output voltage is. Okay? And you will be applying this again and again and again to these types of circuits. And so just like that homework problem, I bet biasing was one of your issues with that homework problem that had all those transistors. And you end up doing something like this, right? You ended up having to make assumptions for VBE and that sort. But just remember, there's only a few things to remember with this. And no matter how complicated the circuit, you just apply the same thing over again. You make an assumption at the very beginning that all the transistors are forward active. You go ahead and put 0.7 volts on all of the VBEs. You look for current mirrors. And if you can find a current mirror, you're probably going to find something that's generating current, like this side right here. You find that current, and then you mirror that current everywhere. You determine the different voltages based on your known voltages, which are the VBE ons, and the voltage across resistors when you know the current going through them. Yes?
For all the current mirrors, you make the assumption that the counteractive bases are.
Yes, so that's what I'm doing. And so if I wanted to be more accurate, I wouldn't say that this Iref here, right? I mean, I would have to say this is Iref here. That's definitely Iref. But coming here, base current may steal some of that. So I am making that simplification, and usually you can. If beta is 100, you can make that simplification. Even if beta is 50, you can probably make that simplification. Because again, you include those betas. If Iref turns out to be 1 milliamp, maybe you'll end up with 0.99 or 0.98 milliamps or something. Right? You'll be very close if you neglect those betas. And that's close enough that you don't want to mess with those. Okay? But see, this thing's not going to require that much calculation from me at all, right? So if this is, I don't know what the calculation complaints are. Well, I know what they... You can complain about calculation, but if you do it this way, where you end up with just this, now you're just plugging in, 1.4 volts plus whatever Iref is, which you calculate from here, times those two resistors. Very simple calculation. So this is the way you should do it. If you are complaining about calculation, maybe you're doing it in a way that you shouldn't be doing it. Maybe you put the 0.7 volts in from the beginning, and the 10 and the 0.7 and the RF, and then you're calculating all that stuff. Don't do that. Right? Do it all symbolically first. End up with a compact symbolic solution, then plug the numbers in at that time. And maybe some of you are doing that. Maybe our homeworks are more calculation than you think. I think that's probably true too. Because, right, you got to, for a small signal at least, you got to calculate GM and R naught. So that's just the nature of circuit design. You got to get those things. And soon it should become second nature to you, right? Soon you'll just remember, okay, what's 1 milliamp, then GM, that's just 1 over 26 or 1 over 25, right? Any questions about this? Any more questions? Number 1.
Yeah, it was the gain.
With the capacitors?
Right.
Yeah, that we shouldn't have done that. We should have told you zero frequency means open the capacitor, and high frequency means short the
Well, the reason
capacitor.
I was confused is because in lectures 6 and 7, you define
Yeah, I
high
know.
frequency gain and low frequency gain. It's like 1 over 1 plus S or something like that. S over S plus
Yeah,
omega.
yeah,
Something like that.
yeah. Yeah,
So
that,
are those the same idea? Or
they're not. See, the problem you had in problem number 1, that was an effort to try to simplify that for you. But it backfired. Because, right, if we had instead of given you values for those capacitors, which probably we should have done, right, then you would have been able to tell, okay, that capacitor is so big, then at high frequency. And we could have said that this capacitor value is 10 microfarads or so for part A, for the part where you're supposed to treat it as low frequency, right, or sorry, high frequency, right? And then we could have said the capacitor value was 1 picofarad for the low frequency stuff, right? And so we should have done something like that instead of trying to. We thought it would be simplifying it for you, but it wasn't. It was backfiring because there's more a communication issue is what
so
that
then
was.
what do you define the
I'll never throw a problem like that at you on an exam. It would be much clearer than that, right? So that problem just wasn't clear enough in the end, and we admit that. It should have been clearer, okay? Any other issues with this class? Because what I'm learning is that, see, when I taught this in 2009, there was a bit more uniformity in the 105s that you took. In this class, it looks like it's not as uniform. Some people have had some things, some people have not. It's no one's fault, right? Not even the faculty's, professor's fault who taught 105. They just have different styles there. Probably all of our faults collectively that we should probably get 105 to be something more uniform that we can rely on a little bit better. But I understand it's not as uniform, so some of you may not have seen this before. Some of you have. But I just wanted to get this out of the way here. I skipped this because I was pretty much thinking you all knew this. Okay? But get some practice on this too, because I think DC operating points are also very important to be able to get. I'm sort of emphasizing a lot the small signal part of this course, but the DC operating point arguably is the more important thing to be able to get, because you can't get a small signal circuit unless you've biased it correctly too, right? The biasing determines the GMs, the R0s, everything, that then determines all the small signal stuff. Okay? Maybe I'll throw a problem at you at some point that includes a saturated transistor. I know this one has no saturated transistors, right? But I can certainly generate one that you can deal with that has a saturated transistor, so you can experience the inconsistency you get when you have a saturated transistor. Okay? Now, MOS is exactly the same as this. I won't do an MOS example, but it's the same except more difficult because you can't just go in and assume these 0.7 volts. You actually have to calculate the gate to source voltages, and that's going to be done based on the currents going through these devices. Okay, so it's more of a pain in the rear to do the MOS without question. Okay, and in that case, you would have to solve a set of equations that give you Iref and the voltage across the MOS device in this case. Okay. All right. So with that aside, let's go back to what we've been talking about, which are these high swing current sources. And so this is an example of a high swing current. The last high swing current source that we looked at, we liked this high swing current source. Why did we like this high swing current source? Can someone tell me? What do we like so much about it? Well, what about this portion right here? Why are we doing that? You guys remember? Apparently not. The reason why we like this thing right here is because it allows this device M3, right, which is delivering the V bias out of this. So this is the V bias generator, right? I can call that V bias 1. I can call this V bias 2. Right. It's delivering V bias 1 to M1, and it now has a VDS across here, VDS3, that's equal to VDS1, which is the transistor I'm trying to use as a current source that I'm biasing up. Okay, so that means I got a VOV across M3 and I got a VOV across M1. And that's great because they have exactly the same VDSs. That means if I have a certain current I1 going through M3, then I'm going to have that same current going through M1 no matter what the lambdas are for these devices, no matter how large their output resistance is. So I like this current source here. And this is what we ended up with, which is just a simpler rendition of the chain of devices that we used to have here. So in the last lecture, I sort of went through the process in coming up with this circuit. And that was sort of the historical process. That's what people did to finally culminate in this circuit, which gives a nice method for generating a cascode bias in MOS, in low voltage MOS. Okay? And now let's keep that up. And so the final things I want to say about this is all great, but we still have the issue here, and that we still must worry about body effect. Okay? And, if we worry about body effect, then it's the same thing that we've done with the other circuits. We have to design defensively. And design defensively basically means we have to make sure that VGS of 7, which determines this voltage at that point, which in the end determines this voltage right here, which we want to be VOV, we have to make sure that VGS of 7 is greater than a VT plus 2 times an overvoltage of, say, device 3. Okay? And to do that, you have to size the device a little bit differently than what our equation said. So our equation said size it like this. Size device 7, W over L7, to be 1/4 the size of W over L3, which is basically the size of all these other transistors. They're the same size as W over L3. But if I want to defend against body effect, which is, the VTs, the threshold voltages are larger than 0.7 volts or than VT naught because your source is not tied to your bulk. Your bulk is tied to ground and your source is tied to some other voltage there. Then what you want to do is make this device a little bit smaller. W over L, instead of W over L being 1/4, maybe make it 1/5 or 1/6 or something like that to ensure that this device M3 and hence M1 in your actual current source is saturated, not triode. Does that make sense what I just said? Okay, we've been through that a couple times. All right, so that's it for high swing current sources that I'm going to say. And high swing current sources, again, very important topic because we need to make sure we have the maximum swing to maximize our dynamic range. That just means your headphones sound better when you have better dynamic range. Your cell phone will sound better when you have better dynamic range. Okay? And so what I want to talk about right now are more things that might happen for an IC process circuit. Okay? And so let's talk about current source matching considerations. And so what do I mean by this? Well, we know that to make a current source, and I'm going to do all of this in MOS, then I'm basically doing this. So I'm generating a V-bias generator, which is what that is there, just a diode connected with some current source generator, possibly a resistor is doing this, but I'm just going to make it generic and draw a current source there. Okay, and so I'm doing replica biasing to bias up another MOS device that's being used in an actual amplifier. It could be that one. And also to bias up maybe another one here. Call that M1, call that M2. Okay? And so usually in this, we often want to match the currents of those two devices. Because oftentimes we're doing things where we're amplifying using one of those current sources, amplifying using the other one, and then we're going to subtract the two of them. And if we had the exact same signals into those two amplifiers, we want the signal to cancel if we subtract them. Okay, but they're going to cancel only as well as these are matched. So this is going to have an ID1 as its current. This is going to have, let me call them output currents, I01. And that's going to be an I02 for that current there. And I'll just write what I said. In MOS, we often need match current sources. And you'll see this later on when we start looking at actual op amps. So I01 we want to equal I02. Now let me not use not. Let's use D. It looks like a D anyway, so. Because later on I want to use the actual drain current equations. That's probably easier to understand. And so how can we match these currents? Okay, so we know that each of these currents is given by an equation like this. So here's ID1, right? That's equal to 1/2 mu n Cox times the W over L of device 1 times the VGS of 1 minus the VT, except now it's W over L of 2, VGS of 2 minus VT of 2 squared. Okay? And so what we try to do in this case to make sure that these currents are identical is we try to make W over L1 equal to W over L2. Okay, but as you know, we don't always get this. Okay, and we don't always get this. Why? It's because it's an IC process. Right? We have finite fabrication tolerances. In an IC process. Okay, and that's something we're just not going to be able to get away from. We will always have these finite fabrication tolerances. I mean, technology does get better with time, but so do our devices, right? We still get smaller and smaller channel lengths with time, so our technology is up with unable to get exactly the dimensions we want and unable to even match two transistors side by side. So you're always going to have some mismatch there. And that's not just in lithography dimensions, it's also even things like threshold voltages. So these transistors, right, they're not going to have exactly the same threshold voltage. There's going to be some statistical variation just because of the manufacturing process. Okay, and that's what we're concerned about here. Okay, so we're concerned about the fact that these two currents won't be perfectly matched. If W over L1 is not equal to W over L2, and even if VT1 is not equal to VT2. Okay, one thing we can be sure of is that these two voltages here, VGS1 and VGS2, those are equal, right? Because they're right off of the same line type thing. There should be no DC current going into the gates of these transistors, so it's much easier to make sure those voltages are about the same. Okay? There's other things that can happen like noise, etc., which we'll talk about in a second, but let's not think about that now. Let's think about this mismatch. W over L1s are not the same. The VTs are not the same for these two devices. And so we want a way to quantify this. And so to make it easier to quantify, we're going to make some definitions. So let's define average and mismatch quantities. Define them on the other side here. Okay, so an average quantity. For the average quantity, I'm just going to take the average of the two quantities. So for example, I'm going to call it ID. So ID is the average. So ID1 is the current for device 1. ID2 is the current for device 2. And the average quantity is exactly what you think it is. It's just the average of those two currents. Okay, so on and so forth for everything else. I can define an average for my W over L's. This will be 1/2 W over L1 plus W over L2. And then finally for my threshold voltage, something that's going to vary. Like I said, that's going to be 1/2 threshold voltage. Let's keep the bracket there to be consistent. Threshold voltage of 1 plus threshold voltage of 2. Okay, so that's my average quantity. And I'm really just defining variables, right? I'm just saying I sub D is the average, W over L. So the variable without the subscript is an average quantity. Okay? then I'm also going to define a mismatch quantity. And the mismatch I'm going to call delta the thing. So delta ID is going to be equal to ID1 minus ID2. And I'm going to be careful to keep that convention. It's going to be 1 minus 2 for all of these different things. So, of course, I can also define a delta W over L. That's going to be W over L1 minus W over L2. And finally, a delta VT. That's going to be a VT1 minus VT2. Okay? And so from these definitions, I can also define fractional mismatches. So let's take, for example, just the IDs here. If I take delta ID over ID, that's the definition of the fractional current mismatch. Okay, and so on and so forth, right? I can have a delta W over L over W over L. Let me make a better looking delta for you. That's defined as MOS device 1, NMOS device 1 in this case. That you can see is equal to ID, which is this 1/2 ID1 plus ID2, the average quantity, plus delta ID over 2. Okay? So it pretty much works out that way. You can do the math in your head right now. Right? At the same time, I can express ID2 as being equal to ID minus delta ID over 2. Okay, and so on and so forth for all the other quantities. So just to be complete, W over L1 is the average quantity W over L plus delta of W over L over 2. W over L2 is that average quantity W over L minus this delta W over L divided by 2. And finally, that VT, VT1, same kind of thing. So VT1 is VT plus delta VT over 2, VT2, VT minus delta VT over 2. Okay, so everything that I've done so far is just definitions. And the definitions that I'm defining because they will make our subsequent analysis a bit easier to look at and interpret. Okay, so what am I going to do? Let's plug these into the current equation. So here's my equation. ID1, I just said, was equal to ID plus delta ID over 2. Okay, but I know that ID1 is given by this 1/2 mu n Cox times the W over L of 1 that I know that I can express as W over L plus delta W over L over 2. Okay, times VGS minus VT. Okay, and so in this case, VGS is there minus VT of 1, I'm trying to say. So VT of 1 is VT plus delta VT over 2. So this is going to be VT minus delta VT over 2. And that's going to be squared. Okay, and so in this, I can pretty much identify here. This is my average over voltage there, VOV, VGS minus that VT. So I'll just note that now, but not really use it at this point. Okay, so now what I'm going to do is try to expand this. All right, so here I'm going to have 1/2 mu n Cox. Nothing to expand here, so I'll just repeat this down. Now I'll expand this through that square term there. And I guess just to make it easier, I'm going to use the VOV, so I'm not going to write too much. So VOV here squared plus 2 times VOV times delta VT over 2 plus a delta VT over 2 squared. So delta VT squared over 4 is what that ends up being. Yeah, that's right. This should be minus here. So minus that 2 VOV there. Thank you. All right, so in this, I'm going to start killing some things off here because they're going to be small. Okay, so these deltas, right? So right, how much of a difference are we talking about? So VT is 0.7 volts, right? And so there's going to be mismatches between the VTs of these two transistors. Like there's going to be a VT1 and a VT2. So maybe one of them will be at 0.7 volts, maybe the other one's at 0.75 volts or something like that, right? They're not going to be mismatched by that much, but they'll be mismatched. But if that's a very small mismatch, that means delta VT equals 0.05, right? If I square 0.05, that's an even smaller number. So any squaring or multiplication of delta terms, I'm just going to neglect. Okay, so I'm going to neglect that because it's small. So I neglect the small term right there. That just simplifies my expression here. It makes it approximate, but good enough for what we're looking for here. I guess I can also in this thing cancel out these 2's, right, because they're just going to divide each other out. Okay, and so let's go to a next step here. So now what I want to do is multiply through these two terms, the W over L term and this term here, which I've simplified to some extent and made it just a 2-term type thing. So now this is just multiplying 2 binary expressions here. And so 1/2 mu n C ox times, I'm going to get W over L times VOV squared plus my delta W over L over 2 times VOV squared minus W over L times VOV times delta VT minus delta W over L over 2 times VOV times delta VT. Okay, so I end up with this. And again, I'm looking for things where I'm multiplying 2 delta terms, because multiplying 2 delta terms is going to come up with a very small term. And here I see that again. Right here I got delta W over L times the delta VT. So out that goes. Anything else I can eliminate in this? Can't eliminate that. No delta terms. 1 delta term. Can't eliminate it. 1 delta term cannot eliminate it. So the rest of them stay. And now taking this down to another level here, let's just multiply some things out. So I'm going to end up here with a 1/2 mu n C ox times W over L times overdrive voltage squared plus 1/2 mu n C ox times an overdrive voltage squared times the quantity delta W over L over 2 minus W over L over an overdrive voltage times delta VT. Okay? And so I can recognize a couple things here. This I can recognize as just ID. Right? So this expression, this term is ID. So this corresponds to the exact same thing as this, which must mean this term right here corresponds to that. Okay, so now I can write all this out again, taking those into account, where this delta ID over 2 is going to be equal to this 1/2 mu n C ox times W over L, where I'm now factoring out a W over L. So from this, let's factor out a W over L to get to this equation here. And so I have that VOV squared. But when I factor out the W over L, I end up with 1/2 delta W over L divided by W over L minus a delta VT over my overdrive voltage. And usually what I'm looking for now, well, I can see a couple things, right? So I could see that this right here That's just ID. Okay? So I can move the ID to the other side of the equation, and I can end up with delta ID over ID is then going to be equal to moving that 2 over to this side here, delta W over L over W over L minus delta VT, better delta, divided by the overdrive voltage. Interesting equation now, because this is telling me how much mismatch I'm going to have in currents. Okay, so the way to interpret this here is that this is my fractional current mismatch, a quantity that can be used to compare one current source design, for example, with another one, on how well matched their currents are. So that's my fractional current mismatch here. And so this term right here is a geometry-based mismatch. Okay, so a geometry-based component. So it is reduced. Okay, so that means the overvoltage that you're using to bias up your transistors, usually we like to make that overvoltage as small as possible, right? And why do we want to do that? Because it's swing, right? That determines our swing. Our V output minimum is equal to 2 overvoltages. So if you can make that overvoltage smaller, you get larger swing, larger dynamic range. Okay? But, you know, this is a problem for us because today, what's happening today? The supply voltages are going down, right? So VDD in my day was 5 volts, right? Now it's shrunk to 1 volt, right? And why has it shrunk this way? Because analog designers are second-class citizens, right? It's the digital designers, right? It's the digital that people are pushing now, right? Digital is, all the technologies are going for digital at this point. And digital, the smaller transistors, et cetera, they're making the VDDs go smaller and smaller. Okay, so VDDs go smaller and smaller, and that means automatically your overdrive voltages have to get smaller. So with each technology generation, it makes it more difficult to match current sources. Right, so this is just one example of how life gets difficult for analog designers. Right? So just one example. I mean, there's tons of examples that I can throw at you here, but this is a very obvious example based on what we're studying right now. Okay? Now, you may look at this. Okay, I need to address this, right? So this minus sign there, you're saying, okay, wait a minute. What are you talking about here? If I make my VOV smaller, doesn't that make this whole thing smaller? Because that's a minus sign after all, right? But in this kind of analysis, pluses and minuses mean nothing, okay? Because the worst case is that this delta VT is negative. So what you do is you take the worst case, right? So in the end, this VT, that could be negative. So this doesn't necessarily help. This term doesn't necessarily help us. Okay? So you always take the worst case here. Anything that maximizes either of these terms is going to be a problem for you in terms of matching currents. Yes? Can you design it? Well, no, this is a delta VT, though. This is not the value of VT. This is how different VT is from the desired value. So sometimes it can end up being larger than it, in which case it's positive. Sometimes it can end up being smaller than the target VT. So you don't have control over it because it's a statistic. It's a random thing. See, from process variations. Does that make sense? So I'm trying to hit VT as 0.7 volts. I might end up with 0.8 volts. I might end up with 0.7 volts. And so it's 0.7 minus 0.8 or 0.8 minus 0.7. So it can be negative or positive, and you have no control over what it is. Okay? So this is just one of the things that you worry about as an analog designer, especially as you go to these new technologies where the W over Ls are so small, right? The channel lengths now 34 nanometers, getting smaller, that sort of thing. That doesn't give you a lot of room to give yourself buffer for that channel length changes, which then changes this W over L1 versus W over L2, right? The threshold voltages are more difficult to control, etc. So analog designers is just becoming more difficult for you as technology advances here. But that's the excitement in analog design, because that means things stay interesting, right? So, right, if I'm saying things about analog designers, let's say something about digital designers, come on, that's boring. Right? At a certain point, right, it all becomes automatic generation of this, right? You're not laying anything out. You're not worried about W over Ls at all. You're just, using code languages, right, to generate this and that. And so it becomes very simple. It was exciting for the ones developing those languages and stuff, right? But now it's much less exciting. And the more exciting area is analog design, without question, right? You need a problem to have to solve to be happy, right? Now you guys, we're all technical guys, right? We want a problem to solve. And if there's no problem to solve, right, you're going to be bored out of your mind. So you should be happy that the digital technologies are doing this to you if you want to be an analog designer, because it's going to keep life interesting for you forever, right? I have to make sure I say that, because that's true. That's the truth, actually. That is the truth. All right, so that's all I have to say of this course. The last thing that I want to talk about are things like power supply variations and temperature variations. Those are things people are very concerned about as well, but we'll leave that toward the end of the course after we've learned more about op amps and how to design those. So that's what I want to do now. I want to move to talk about the design of op amps here. And so let's get back to this lecture here. And so this I'm going to do, at least initially, with some prepared notes, mainly because this is one of those things that I believe you've had already. I've been known to be wrong about those things before, so if that's not true, then you can stop me and have me slow down. But I'm pretty sure this part in the beginning you've had, because we actually covered this in the first day, a little bit of it. Okay, so this is a little bit of review. So what I'm going to do is talk about op amps. Actually, I have that in my other thing here. Let's pull this up one more time. Here. So this is what we're going to do. Okay, and op amps is going to take us the rest of this course here. Because the op amp is the workhorse, like I said, on the first day of pretty much all analog circuit design. Whether it's on off-chip stuff that you can see with the naked eye, or whether it's all on-chip. They all rely on op amps. And so what do? We're going to talk about ideal op amps very quickly, sort of review of sort of what we've already gone through. Then we'll start talking about differential pairs, emitter-coupled pairs, something that I believe you've seen before. I see smiles, but I know you've seen that before. Offset voltages, maybe you've seen that, maybe not. Then we'll start talking about gain in op amps, finite gain. Two-stage op amps, let's talk about the design of op amps. There's single-stage, there's two-stage op amps. Some of them use cascode, some of them don't. Finite bandwidth. Okay, these are all non-idealities in op amps. Stability. And when you put these in a feedback circuit, it's not automatic this is going to work. The stability may be one of the most important things to be able to do when you design and use an op amp. Compensation of op amps. If you find your op amp is unstable in a certain feedback circuit, there is something you can do about it. But you have to understand pole zero diagrams. You should understand to some degree root locus plots. How many actually understand these things here? Pole zero and root locus plots. Okay, maybe root locus isn't that important, but pole zero, come on, pole zero diagrams? Yeah, left half plane, right half plane? Okay, good. Slew rate, how fast your op amp can actually keep up with a certain square wave. Of course, very important stuff. Sounds like a digital thing, but it's really an analog sort of thing, because you've got to go from analog to digital. It's an op amp that will generally make that transition for you, so the op amp has to be able to put out a nice square wave by the end of that. Settling, power supply rejection, this is a noise issue, settling time, and then single-stage cascode op amps, I should say, for better bandwidth performance. Okay, so it's going to come down to getting the highest gain bandwidth product we can possibly get with an op amp. So some of the above is review. We'll do the review material using my made lecture notes, which you're seeing right now, so these right here. And then when we get to stuff that I think you haven't seen, I'll slow down again and start writing things out. So, ideal op amps. Right, so first of all, what about the concept of an ideal voltage amplifier? So what does ideal mean to you? So it's ideal when your gain from your source voltage Vs to your output voltage V naught is equal to A sub V. Okay? And so, in other words, it's ideal when the source and load resistors cannot influence the gain of the amplifier. That's a definition of an ideal voltage amplifier. So for this to occur, you have to eliminate voltage division that occurs at the input and output when you have a source resistance and a load resistance. And so this happens when your input resistance is infinite for your op amp and when your output resistance is 0. Okay, so what do I mean by that? So if I had to draw that out, let me go 1.5. So say this is my amplifier with a gain A sub V. And these notes, by the way, are going to be online. I guess they're not online just yet, but I'm not going to finish this, obviously, today. So you'll be able to print these out and use it for the next lecture. And just run along with me with the next lecture. But usually this is what we're looking at, some amplifier driven by some kind of source voltage here, some kind of source resistance, some kind of lot. And basically, the whole gain across this is going to be R sub I over R sub I plus RS times that voltage gain times R sub L over R sub L plus R naught, and that's the gain. So obviously, if Ri is infinite, this becomes 1. And when R naught is 0, then this becomes 1 as well. So your gain just becomes A sub V. Right? So that's why we want Ri to be infinite, R naught to be 0 for an ideal voltage amplifier. Okay? And so naturally, if that's an ideal voltage amplifier, then this leads to our concept of our ideal operational amplifier, where the operational amplifier just differs from the voltage amplifier in that it has a differential input. Okay, so there's a question, why do we want that differential input? We'll talk about that in a second. That has to do with noise. Okay, the differential input actually knocks out a lot of circuit noise that otherwise would be there if it was not differential. And so it's almost like life, right? We like things that are symmetric. Things that are symmetric are always good for some reason. And that has to do like your glasses, right? If I had a star on this end and a circle at that end, it wouldn't look good, right? But if they were exactly the same like this, it looks better, right? People like symmetry, and it turns out in design, symmetry is great. And so that's where these op amps come in. They sort of borrow from that sort of reasoning. And so in general, for an op amp, you're going to have 5 terminals. Okay, you're going to have... okay, yeah, we'll look at some of those things, like push-pull and stuff. That's going to be like an output amplifier type terminology. We will look at that, yeah.
Okay.
Yeah, you'll see that.